All right, this is simultaneously hello and goodbye. We are starting the last lecture of the week. So let's go ahead and get going. So we had this sort of 5-step process for model building greatness. As we may recall, the 5th step was evaluating the reliability of your model. This is a big deal. This is a huge deal. This is maybe one of the things that help separate a statistician from a non-statistician. There's lots of ways of doing this. So checking the reliability of your model can be done in a whole bunch of different ways. This is also sometimes called validating your model. We're going to talk about one way of doing it. This is the way that our textbook emphasizes it. However, like most of the other ways are kind of variations, tweaks, improvements of kind of what we're going to talk about right now. So we're definitely getting kind of some of the core principles or kind of central ideas. So what is this idea of reliability? This idea of reliability is basically trying to determine how well our model will handle future predictions, right? Typically, right, if our goal is prediction, and so right, if we're measuring reliability, we're kind of assuming that we do have this sort of goal of doing predictions. Then we sort of expect that we're going to get more observations down the road, and those additional observations, we want to make predictions for what their y variable is. How well is our model going to work in terms of doing that? Now, at this point, we should have picked our best model. So like all the other steps should be behind us, right? We should have figured out what our best model is. We should have made sure that it's passed all its diagnostics. We've checked the assumptions. We've checked collinearity, right? All this stuff is done, and now it's time for this last step to assess and address our model's reliability. So how do we do this? Our book talks about 2 approaches. I'm not really sure how often that first approach is used in practice. But I mean, certainly it could be done in theory, right? That is, we could always assess reliability by using our model to make predictions in a follow-up study. So, right, one way to see how well our model works is to actually just wait until we actually use it. Now, of course, if our model is really bad, it might in some way be too late, right? That is, we use it and we get a bad prediction that may or may not cost us. That may or may not be like public health ramifications. And then we use it again and it's bad, and now we're like, oh man, now we screwed up twice. We may or may not get fired. But all right, we could actually just sort of wait a while and use our model and see what happens. But it would be nice to know in the moment. It would be nice to know in the moment how well our model would do in generating predictions. And kind of the key idea when I say future predictions is how well it will generate predictions for observations that are not in our data set. That's kind of the key idea, right? Because if we think about it, our model is sort of optimized based on the observations in our data set. So we could always look at like things like model residuals, and we could see like how well our model predicted observations in our data set. And usually it'll predict them well, but that's a little bit like cheating, right? Because we built the model specifically for the observations in our data set, right? A more interesting question is, how well would our model do for observations not in our data set? And that's the idea of this kind of reliability. So we could just build our model and wait down the road and use it and see how it works, and may or may not come back to bite us. Or we could do something referred to as a split sample analysis. And that's what we're going to spend the remainder of this PowerPoint talking about. A split sample analysis works like this. We take our sample, We take our data set and we split it into two groups. We have a training group and we have a holdout group. The big picture idea is that we're going to use the training group to determine what our optimal model is to build our model. And then we're going to apply it, we're going to test it on the observations in our holdout group, right? The observations that were not used to build the model. Kind of a clever idea, right? And the process where we do this is referred to as cross-validation. Like I said, this is often referred to as validating your model. And part of this cross-validation is the creation of this shrinkage metric or shrinkage measurement that becomes a way of measuring our model's reliability. Do we kind of buy the idea of kind of like why measuring the reliability is like an important thing, and like why it's important to see like how well our model works on observations outside the data set? Like sometimes like it is possible to build a model that's like we might say it's like over specialized to your data set. Like imagine this, like probably should have put together like a quick little graphic, and I'm sorry I didn't. But I think your imagination's up to the task. Imagine like 3-4 points, and they kind of like look like a line. Like the 4 points aren't a perfect line, but they're all like really close to a line. Like your eye looks at these 4 points and you say, oh yeah, like they're making a line. But again, you can't draw a line that hits them perfectly. You can draw a line that's really close to all 4, but not quite perfect. Like our human eye can see that and say like that's a linear relationship, and a line, right, is going to fit like our imaginary 3 points or 4 points very, very well. Well, let's say 3 points. However, right, it does turn out that for these 3 points, we could actually fit a quadratic model that will exactly hit all 3 points, right? So imagine 3 points that look like they're approximating a line. In theory, we could actually fit a quadratic that would fit them perfectly. So what have we done? We've built a model, a quadratic model, that fits our data, these 3 points perfectly, but probably will not fit any other point, right? Because that quadratic curve is going to look dramatically different than the line that those 3 points appear to actually be approximating. Sometimes this is referred to as like fitting the noise in your data. And that's what's tough, right? Are we fitting like what's the sort of underlying true theoretical relationship? That's our goal. Or are we just fitting kind of just like the random noise, and just kind of the fluke happenstance that just happens to be occurring in our data set? And really the only way to kind of determine that is to kind of go through this process of cross-validation. So what is cross-validation? Cross-validation, we first use our training data set to come up with our best model, and we compute that model's R squared. We then use the regression coefficients from that best model to predict values for our holdout sample. Now, this is where that idea of generalized R squared comes in handy. Remember, our last lecture before our first exam, we talked about this idea of generalized correlation. You remember that? And we said that R squared is literally defined as, can be shown to be, the square of the correlation between the actual values and the predicted values. So with that definition, we can compute an R squared for our holdout data set, right? Our holdout data set has actual observations. Based on our model from our training data set, we can come up with predicted values. And then we can calculate that correlation and square it. So we have an R squared from our training data set, right? That's kind of like the best case, like the optimal R squared, because it's based on a model that was specifically fitted to that data set. And we can compare that R squared to the R squared of our holdout data set. And the R squared from our holdout data set will probably not be as good, but it will still hopefully be close. And by looking at how much that R squared deteriorates from training to holdout, helps us see how well or not so well our model does at generating predictions for observations outside the data set. In fact, what we do is we look at the difference in these R squareds. We call that shrinkage. And we use that shrinkage measurement to say how reliable our model is or isn't. One set of rule of thumbs, I'm sure others exist out there. One set of rule of thumbs is a shrinkage less than 0.10 is seen as reliable. A shrinkage greater than 0.90 is seen as very unreliable. And there's an awful lot of real estate between those two numbers, right? Now, that means your very first step, actually, before you start modeling. And so this is sometimes a little tricky to see because it's like the last thing we're talking about. But the first thing we do before we start building a model is we have to break our data set into these two groups. And so the question that we have to answer is, how big should each group be? Right here I say how big should the training data set be, but that also dictates how big the holdout data set is, because that's just what's left over. Now, I haven't really been able to find any consistent rule of thumbs regarding this. You do want to try and make sure that you can satisfy your desired sample size requirements. Right? So remember, so how large it is going to kind of depend on, or how big your training data set is going to depend a little bit on just how big your overall sample size is, as well as how many variables are in your model, right? So, I mean, you definitely want to have, if you absolutely can, you want your training data set to have at least 5 observations for every variable that you are going to have in your maximum model. So that would be kind of, to me, like the key priority. And then if I can, maybe I would actually try to have 10 observations for every variable. And then, right, my sort of leftover observations, I would then hold out for my holdout data set. All right, so let's go back to these bears. Our maximum model had 88 variables. Here I did, and I've seen this done in practice, I did a 1/3, 2/3 split. Again, to me, the most important thing is building a good model. It doesn't matter testing a model if I haven't built a good one. So I have seen half and half splits. I prefer like a 1/3, 2/3 splits. Again, assuming that 2/3 is large enough. Right, so if I do a 1/3, 2/3 split, I still have roughly 8 observations for each variable. So I'm still in pretty good shape. And that still gives me a nice amount of observations, 33, on which I can sort of test my model with. So how do I do this splitting process, right? So I now have 99 observations, 66 are going to go in a training data set, 33 are going to go in a holdout data set. How do I actually do this, right? I want to do it randomly. I don't just take the first 33 and then the last 66, because right there my data set may or may not be ordered in a certain way, and if it is, it's going to create like a bias, right? I'm going to have like maybe all the males in one data set and all the females in another data set, for example. So to avoid doing something like that, I'm going to randomly put people in data sets. How do I do that? Well, I first, right, this is just one of many ways, but it's a pretty easy way. So first I do this ran_uni. The ran_uni function generates a random number between 0 and 1. That 2008 is referred to as a seed. I'm sure the great Professor Rieger's talked to you about seeds. A seed is basically just something you could put in the randomization mechanism that every time you run it with the same seed, you'll always get the same results. Sadly, I don't know that he realized that, but that seed's really dated these lectures. You could see, at least, I mean, I'm always updating the slides, but you could see this particular slide, or at least the code from the slide, came from quite some time ago. Also shows you, I guess, the timelessness of SAS coding, that it's still relevant. So that 2008 is just a seed. It's basically going to generate a variable called ran_num, and that ran_num is going to be some number between 0 and 1. Now I can then proc sort my data by this random number. That's essentially like taking my data set and like shaking it up, shuffling it up. Now I have this shuffled data set, and now I can do something like, okay, let me remember. So there's the data step. Remember, we could do something cool in SAS. We could actually build 2 data sets with 1 data step. So I'm building a holdout data set and a training data set. I'm bringing in that split data set, which is just the bare data set with the random number added in. I do counter equals underscore in underscore. Underscore in underscore is just like a special term inside a SAS data step that refers to observation number. So I'm just creating a variable called counter that's essentially the observation number. And so it says, if counter, the observation number is less than or equal to 33, then output to the holdout data set, else output to the training data set. Pretty clever, right? I mean, straightforward. I don't think it's really anything we haven't seen and probably even implemented to some extent in Stat 511, but just a little bit of a refresher for us, because I know 511 was a while back. Right, and so here's what our data set looks like. You can see that counter variable, just it matches the observations. And then you can see the ran_num. You can see kind of how it was sorted. Now, I'm trying to keep like this particular PowerPoint simple. So I'm going to stick with the model we derived last PowerPoint, which was length, chest, and chest squared. This is technically cheating, right? Realistically, we should have split our data set before determining the model. Are we okay with that? Like, again, like I've tried it in different ways. Trust me. Pedagogically, it's smoother to talk about reliability at the end of the process, even though technically to be able to assess reliability, we need to actually have split the data set at the very beginning of the process, right? So again, keep in mind, technically we split it at the beginning. Now, the R squared of a model with length, chest, and chest squared is 0.9665. Right, so here it is. And again, I'm running this model on my training data set. We can see on the top that that's just a 66 observations. So, right, this model does appear still significant. And 66 observations, R squared 0.9665. Now I need to find the R squared for my holdout data set. So, right, you can go back and look for yourself where I create that y hat underscore h, right? The predicted values underscore holdout set. Those numbers, the 38, the 12, the 3, the 0.29011, those numbers came from the previous slide. They're the model that was determined by my training data set. So I'm creating predictions for the observations of my holdout data set based on the model from my training data set. Okay, so now I have the actual y. I have the actual weight. I have the predicted weight. That's y hat underscore age. So I can find the r squared by looking at their correlation and squaring it. Now, right, be careful. I've seen in the take-home test, it's very common for students to just take the actual correlation from proc core. You have to take the correlation from proc core and square it. Because we're working with a number between 0 and 1, squaring your correlation is actually going to make it smaller. So sometimes like your red flag is like you think that the correlation is what you should be comparing to the r squared, and you say like, man, my r squared has gotten larger. That should pretty much never happen. So again, don't forget to take the value from the correlation and square it. In this example, I took the value from the correlation, I squared it, I got 0.9625. So it's the cross-validation correlation. It's the r squared for our holdout data set. Our shrinkage then is the original r squared, 0.9665, minus the r squared from our holdout data set, 9625. That's 0.0040, which is quite a bit less than 0.10, indicating that this particular model is very reliable. It's highly reliable. All right. Now, for better or for worse, you actually have at this point all the knowledge and skills you need for your take-home test. And so probably that's being assigned right now. And so that's what you want to kind of gear up and start working on, right? These last few lectures, particularly this one on like the best practices on model building, which have tied together everything in this course. We're now ready to take a quote real life data set and build a model and see how well it works. So pretty exciting stuff. I'm real psyched for you. So now it's time for you to roll up those sleeves and get to work.